I'm admitting everyone joining in, so I'll just give it a few more moments.
Hello.
All right, well, welcome everyone to Remoticon 2020. My name is Bruce Dominguez. I'm one of your room moderators here. And depending on your time zone, good morning, good afternoon, and good evening. Today, Shawn Hymel will be hosting a discussion on tiny machine learning. And if you have any questions or comments, please post them in the chat to the room. And, you know, it's a community, so definitely be involved, respond to each other. And with that, Shawn is an electrical and embedded engineer, a freelance content creator, and he and Harris Kenny host a podcast, the Hello Blink Show, where they discuss various aspects of starting a business, from sales to hiring. And Shawn has created his own company, Scalriza, that helps companies create compelling technical content in electronics and embedded systems. And Shawn is an advocate for enriching education through STEM, and he believes that the best marketing comes from teaching. He can be found giving talks, running workshops, and swing dancing in his free time. And with that, I'd like to introduce you to Shawn Hymel.
Awesome, thank you, Bruce, and welcome everyone. I know that we still have people kind of trickling in through their waiting room here. As Bruce mentioned, I have been doing a bunch of machine learning recently, mostly in the embedded world. I used to work for Sparkfun Electronics. If anybody ever watched that channel, I wear my bow tie and I'm doing it today, so nice recognition there. I got to keep the brand going. And one of the things I've been doing for the last year or so is learning machine learning. I'm going to take off my glasses. You'll have to forgive me as my room gets a little toasty here. My glasses are going to fog up. So normally I do actually wear glasses. They're not fake, but since I'm nearsighted, I'm going to take them off so I can look at the computer. So we're going to be doing machine learning, and machine learning specifically for embedded systems. And I've asked people to pick up some hardware if you want to follow along. If not, I believe these are going to be recorded so that you can come back to them later. And I will continue to produce content out there on the internet about how to, you know, say, get some type of machine learning thing running on an Arduino or running on an STM32. I've asked people to grab an STM32 L476RG Nucleo board. Mostly because that is what I'm familiar with. I have recently learned how to get this running on an Arduino board. That's a little easier, but when I made this workshop, I'm going with what I know. So let's jump in because I know that there's a lot to cover here. Let's click share screen, share. Hopefully everybody can see that. And it looks like Bruce just dropped in the Hackaday project link. So if anybody wants to take a look at that. And I'm going to go ahead and share this. All right, hopefully everyone can see this. If you have not done so already, please solder the headers to your microphone breakout board. Do that while we're talking. Please install STM32 Cube IDE. Just Google search that term, download it, install it. I think you're going to have to sign up for a account on ST's site. So heads up on that, accept all the defaults. It's a pretty large download, so please do that if you have not done so already. You will also need some kind of serial terminal program, like I'm on Windows, so PuTTY it is. Forget what the big one on Mac is, but you've got like Serial or a couple of others on Linux. The other thing is you will need to create a Gmail account if you don't have it already, and you will need to create an Edge Impulse account. We will be using not Gmail necessarily, but we're using Google Colab, which will let us run a script that I wrote to help us curate the data. And we're going to be sending that curated data up to Edge Impulse to help us do the training. I chose Edge Impulse because it's a tool, it's a graphical tool. And honestly, if I just gave you Python scripts to run the training, it would be doing the same thing anyway, that you're just running through this script that I've provided to you. The advantage of Edge Impulse is that they manage all of the packaging up in libraries for us so that it runs. I'm going to do my best to make this not a canned demo so that when you get this library, I'll show you what you need to use in that library for your embedded system. So yeah, the worksheet is on this GitHub link. And there we go. The worksheet is on this GitHub link. Please go there. We're going to be working out of that. Please feel free to work ahead. I really don't mind. In fact, I can't see a lot of you right now. So if you're like, chomping at the bit, go for it. Start working ahead. I will say if you run into problems, wait until I get to that point where I'm also working through it, and then I'll try to catch up in the chat. However, please use the chat. Please ask us questions in chat. And if you see somebody else asking questions, please try to help out if you've run across this problem. I know on Twitter, a few people were running into problems uploading code. If you use the demo program that we're going to go through in my GitHub repo, then it should work. All the settings are there so that it uploads to the Nucleo with no problem. I have released these slides as Creative Commons, so if you want to pick and choose some of them and talk about tiny machine learning in your own company or with your own community, please do so. I really don't mind. All I ask is for a little bit of credit. So what is embedded machine learning? Something I have learned fairly recently. So the class was called TinyML. And what's the difference between TinyML and embedded machine learning? Well, what I've learned is that TinyML is developing as this community. You can go to tinyml.org and sign up for their talks. They do them like once a week or once every other week. There's a forum where people are discussing running machine learning algorithms on an embedded system. So things like single board computers and more specifically microcontrollers. So TinyML is the community. Embedded machine learning is kind of considered the general broad concept of let's run machine learning on embedded systems. So why do we care to do this, right? We've got these giant computers and servers out there that already do machine learning for us. In fact, they do it really well. Any number of Amazon and Google services, Netflix recommending to you what movies you should watch. That's machine learning. So why do we care to run it on an embedded system? Well, let's take an example here. You are probably most familiar, many of you probably have one of these devices sitting in your home right now, and that is the Echo, the Amazon Echo or Google Home or whatever, or even your smartphone for like, hey Siri, that kind of thing. Most of the time, when this thing is interacting with you or you're interacting with it, it is streaming audio data to a server. So we'll go with the Echo here. That's streaming audio data to an Amazon server. However, it's not always listening. It's not always streaming data. It's listening in tiny little chunks up front for a specific keyword. And for the Echo, initially by default, that's Alexa. That is the keyword. That listening for that keyword happens on the device itself. It's a microcontroller that's doing embedded machine learning, TinyML. When it hears that keyword, then it opens up a stream to the Amazon servers and just starts piping anything it hears after that, where more complicated machine learning algorithms take place that do things like natural language processing in order to determine. Yes, I'm so sorry to everyone that just heard that word and all of their Echo devices started beeping at them. I apologize. I will refrain from using that word as much as possible. In this day and age, it's almost like a curse word if you're streaming stuff. So once it opens up that socket to a server, an Amazon server out there, that's where all the natural language processing comes from to determine what you're trying to ask it to do. That's an example of embedded machine learning. Other kind of things you'll see are things like video object detection on a very, very low level, like a person detection. This is not trying to do like, self-driving cars. We're trying to identify every object and roads and what have you. This is more like, oh, I just want to see if a person's in the frame. And in fact, I've got a security camera that can do exactly that. And it's a microcontroller doing this. Something else that I've seen is anomaly detection. You take sensors like accelerometers and you put them on like, I don't know, a servo or a motor or something that's going to give you some type of vibration data, and you watch that over time, and then you say, okay, is there an anomaly? Is this thing about to break? That can be very, very helpful for things like Yeah, washing machine. Washing machine is another good one. Is this about to break? Things like satellites, right? Where things you can't get to, you need to know beforehand so that you can take actions to prevent the break from happening in the future. You can be a little predictive with this, which is where machine learning comes in. And that's why we want to run this on embedded systems, because it allows us to do these kinds of things. So if you didn't get the link already, here is the GitHub link to my keyword spotting. That is going to be our worksheet. Start working through that. I will work through it with you as we go through this, but I will also stop and explain things. Bruce linked it, so please click on that. Thank you for that. I will continue to talk about concepts as people are working through this. When we get to a stopping point, that's a good place for me to blab some more and answer some questions. And there'll be like specific slides for that kind of thing. Once again, I mentioned that I'm going to do my best to not make it a canned demo because that's annoying. I want to give people the tools they can use to create their own, say, keyword spotting system and introduce them into the world of embedded machine learning. Data collection. The first thing we need to do is data collection. So we're going to head to this script. I'm going to exit out of these slides. Here is the worksheet. And we're going to scroll down this worksheet. Feel free to read this at some point. There are two ways to do data collection for this script this curation script that I made. The first is to do it locally. You'd have to install a whole bunch of Python and packages and stuff to make that happen. So we're not going to do that. I created a Colab script for you. So if you could just click on this Open in Colab button. In fact, let me make that a new tab. So we've got this Colab script. If you've never run Colab before, it is basically a Jupyter notebook. That's all it is. It's Jupyter notebook running on a Google server somewhere. We have access basically to a full Linux box here. Obviously they restrict you in what you can do, but the idea is we can actually like upload files, look at the file system and run Python scripts. And it's giving us a Jupyter notebook interface to do it. To run a cell. So each of these is considered a cell and they can run individually. To do that, we hold Shift and press Enter. I'm sure there's a button somewhere to do this, but this is how I've been doing it in Jupyter Notebook. Feel free to read through this. However, we are not going to be uploading our own keyword samples today. This script does allow you to upload your own keyword samples. Something you can do is take your cell phone, any recording device, your computer, and record yourself saying some keyword. If you were at the Bring a Hack last night, I showed one where I recorded myself saying trick or treat a whole bunch of times, right? That could be a keyword. A keyword doesn't have to be one word, it can be a phrase, but in our case, as long as it's less than a second, that will act as a keyword for us. You need probably about 50 samples, hundreds better, thousands is even better than that. And you want them to be a variety of pronunciations, accents, genders, voices, types, anything you can think of. The more variety you have, the more robust model you're going to be able to create that it will recognize other people's voices. In fact, I've got a good story about this. I went to my parents' house to hand out candy to kids on trick-or-treat night, right? Halloween, because it's something fun to do and I like giving out candy to kids. And I brought this pumpkin hack with me. And because I only trained it on an adult male and an adult female voice, it did not pick up the little kids saying it because they have very different voices. So keep that in mind when you're creating this type of system. For a demonstration purpose, yeah, your own voice is fine. But remember, if you're going to deploy this, think about people might have different accents who are going to talk to this. And that's going to be a problem if they can't interact with your device. And in fact, Amazon used thousands and thousands and thousands of samples to get that ALEXA keyword going. All right, so let's execute this next script. This is all text, so not much is going to happen. Here's where the magic starts to happen. Let's Shift Enter on Node.js. Uh-oh, the notebook was not authored by Google. We're going to run anyway because it's part of my account, and I'm going to tell Colab to run it. This is going to take just a moment. We need to install the latest version of NPM, which is the JavaScript package manager or Node package manager. In order to run the Edge Impulse Uploader tool. It's a command line tool, we'll install it, and that's gonna allow us to just send our data to the Edge Impulse servers. So the next thing we're gonna do here is we're gonna install these packages. So we're gonna install SoundFile, which lets us read and write WAV files. That's gonna be needed by the curation script. And we're also going to install the Edge Impulse command line tool. Once again, that will allow us to we're going to curate a bunch of data. When I say curate, we're going to take a data set from Google. We're going to mix in some background noise, pick the samples, pick the classes of the words that we want as keywords, 1 or 2 of those, and we're going to create a new data set that's a subset of that that's been mixed in without all of the with the background noise, and we're going to send all that to Edge Impulse. Question about Python. Whatever's default in Colab right now, I believe it is Python 3. I thought I printed that out, but you should be good with Python 3, and that should be what's running in Colab. If you have not, just for me, I forgot to check this. Change runtime. Here we go. We're not doing machine learning, so I don't think we particularly need a GPU runtime since we're not doing any machine learning on this Colab right now. So we're just using this as a curation script. So we don't need to worry about a runtime. We're just going to do the CPU runtime. These are some settings that you can modify if you wish, but I recommend leaving them alone for right now for this particular demonstration. Feel free to look through here. We're going to download the Google Speech Commands dataset, which is just a pre-made dataset for us. There is verbiage in here. If you go up to show you how you can modify your own or add your own keywords to modify that dataset. You will want to use the Google Speech Commands dataset and then add your own on top of that. And I'll show you why in a minute. This also allows you to pick the output number of samples, your word volume, your background volume, your sample time, we're going to be using a second, and your sample rate of 16 kilohertz. Also your bit depth, all these things which are juicy good stuff that we're going to need to train our machine learning model with. The reason we set them this way is because we want to look at the microphone. So we've got our, I know I'm probably small, but we got the microphone in the attached to our Nucleo board, and that microphone samples at 16 kilohertz. And it gives us, actually that microphone gives us 24 bits, I believe, but we're going to truncate that to 16. So with 16 kilohertz sampling at 16 bits PCM, knowing what our microphone is, that's what we want to have all of our samples be when we go to train it. Otherwise, there's going to be a mismatch when we go to deploy our neural network. All right, let's run this, which doesn't do a whole lot. It just sets a bunch of variables. And then we're going to say, hey, go ahead and download the Google Speech Commands dataset. And this is going to take a minute or two. What we're doing here is we're downloading the Google Speech Commands dataset from this link here, http download tensorflow.org, and it's going to be downloaded not to our computer but to this server right here. This is attached somewhere across the internet, and let's go take a look here. When we go to start running the curation, we're going to talk about how this curation actually works. So I'm going to give you a preview here because we're going to need to make an account on Edge Impulse first. So so we actually have to do that next. So while this is downloading for everybody, so yeah, I'm going to jump in back and forth between my slides because my slides are for you, also for me to remember what I need to do next. So if everybody has the STM32 Cube IDE, make sure you're installing that or have it installed. We need to create an Edge Impulse account. So go to edgeimpulse.com, sign in, create your account, and we're going to click Login here. And we're going to create a new project. I'm going to call it speech recognition or keyword spotting, whatever you want to call it. And I'm going to call mine, I don't know, 01. Uh-oh, I already have one named 01. It's called 02. Good version control right there. All right, so we're going to go to speech recognition 02. We're going to click on that. And then up at the top, we want to find keys. That little tab that's just on your dashboard, and keys. This is our API key. So double click on that and we're going to copy that. Don't worry if you double click and you don't see the rest of it. It does copy the whole thing. We're going to go back to our script. It looks like it is done. So extracting done. And actually, one second. So we just ran that. All right, so if you click on the folder icon on the left side of Colab, you actually get the file system. In fact, you can go up a folder, and if you've ever used Linux, this should look very, very familiar. Our essentially home directory, where we're going to be working in, is this content directory. So I recommend taking a peek in there, and these are the files. So we just downloaded the speech commands dataset, and we extracted it, or untarred it, rather. And what you see is all of these files, which contains a whole bunch of WAV files. The first thing we need to do is extract the background noise out, because my script that I wrote for the curation does not take kindly to background noise being in one of these input directories. So that needs to be its own separate directory outside of that. That's all this cell does. So let's go ahead and run this cell. And then we are going to refresh your file system. And you'll see that it pulled the background noise category out. So Google Speech Command Dataset gave us samples of the background noise. Great, we can use that. Feel free to also add your own. Your air conditioning running, like, because mine's very loud. You're in a crowded room. Take a minute of recording, make it a WAV file, drop it in there, and my script will automatically extract pieces of that background noise to mix into your keywords later. So let's go back into this real quick. I'm going to open up the background noise, or excuse me, not the background noise, the backward keyword, and I'm going to say download. So feel free to download it and check it. So we're pulling in this file from Colab. And I've got Winamp not wanting to play nicely because it really whips something. So I don't know if people can hear that because it's my system audio, but feel free to play one of these and you should hear the sound being played. Somebody providing a sample of back or backward or whatever the keyword is. And feel free to try any of these. And it's just people saying this word. And there's like 2,000 samples in each of these. It's a pretty big data set. Once again, you can add your own if you wish. If you want to say, record yourself adding these and add it to it. So this allows you to download my personal custom data set that I've been working on. It's mostly a bunch of garbage in there of like, Trick or Treat, Hadouken, Dracaris, just me playing around and just adding to this. It's somewhere on GitHub. So it pulls it in, but we're not going to do that today. We're just going to stick with the Google Speech Commands data set. This is where you want to change some stuff. So we've got the custom dataset path. We're going to leave this empty because we did not create our own custom keywords as part of this. Next, where it says the EI API key, we're going to go ahead and paste that right in that we copied from Edge Impulse. Now, let's pick some words. We want to look at the available words for us. Initially, as a demo, I said stop and go. That's pretty simple, but let's try house. And let's go with 0. That's just 2 words here. Where's the API key? Very good question. So you have to log into Edge Impulse, create a project or go into an existing project that you have. You want to go to Dashboard and you go to Keys. And then it should be right here. So you can just double click that and copy it. That's where you find your API key. Good question. Thanks for the reminder to go back and show where to get that from. Maximize window, it's truncating. So it is truncating this. I can't make this, my window is maximized. I'm broadcasting at like 1920 by 1080 so that everyone, it's a 1080p stream. It does copy the whole key. So even though it looks like it's truncating here, when you paste it in, you get the whole key. It's just a weird thing. So anyway, we've got house and 0 as our keywords. For you, pick house or 0, pick 1 word, pick 2. What I have found is that picking 3 or more, the machine learning model is not able to quite keep up when we start getting bad classifications beyond like 3 or 4 keywords. You can make it 10 and see if it works. I can't promise the model's going to fit on your microcontroller or that it's going to be very accurate. The other thing that I found is that keywords work better when you have multiple syllables and you've got various sounds like consonants and vowels all mixed in there, which is why Amazon went with ALEXA. You have OK Google. It's multiple syllables rather than just like, hey, because that sounds like a lot of other things humans can say. So what I've done is picked house, which is a single syllable. We'll see how that works. And 0, which is 2 syllables. The more syllables you add, the better accuracy you're going to get for that keyword. So pick 1 or 2 from the list over here. If you have time on your own, if you're going through this, feel free to try creating your own and create a custom keywords set that you add into this. And then, so we're going to run that one. And then we are going to download the curation scripts, which is just on that, it's in that GitHub repo that we're using as the worksheet. So I'm going to go ahead and refresh this. Dataset curation, you can double click to take a look. I MIT licensed this, so feel free to use it. And it's just pulling in WAV files, mixing them with background, yeah, and then spitting them out in a data set that's going to be useful for us. So you should have gotten to this point, and now we're ready to run the actual curation. So we're going to shift enter to run this. And this is going to take about 20 minutes, 15 to 20 minutes. So I'll come back and continue to check on this as we're going through. And I'm going to talk about kind of what's going on, why we need to do data curation here. When it says mixing unknown, it is just putting random other non-keywords. Yes, that is absolutely correct. And I've got a graphic for that. So while that's going, because I wanted to get to that point of having people run this script, because it's going to take a while. I'm going to go back to my slides here and talk about exactly what's going. Oops, that is definitely the wrong button. I don't know why Control F5 doesn't work for me, but it does not. All right. So what we've got going on here with this script, and that is a very good question. Oh, no such file or directory. Let me make sure.
Was I supposed to add a link higher up in the, like
so,
in a higher, yeah.
So if you go up,
the custom dataset path is blank, correct?
Custom, yes, that is correct. Custom dataset path should be blank. I'm trying to remember where I put this. There should be something that, here it is. Make sure you've run this cell. In the Google Speech Commands dataset. Got it. If you see background noise, it should be pulled out of the Google Speech Commands dataset. It should be on the same level. The folder should be on the same level. Otherwise, it's considered a keyword, and that's not what we want.
Got it. Thank you.
Sure. Target word cheese is not found in the subdirectory. That is because you need to pick from the available keywords in the Google Speech Commands dataset. So if you, on the left here, if you drop that down, these are the available keywords you have. Yeah, so I don't have the time to show people how to create their own keywords, but if you sit there and record yourself saying cheese like 50 times on your cell phone, and then take something like Audacity and create 1-second snippets out of that, you can then create your own keyword. It's not that hard to do. It's just time consuming, and I didn't have time for this workshop, but that in the GitHub repo, there is the walkthrough that shows you how to do that. You need to go into Audacity, create these 1-second snippets, and then you add it in as a custom keyword here, and you can create your own custom keyword. So yes, you can definitely get cheese in there, but for now, for this workshop, please select 1 or 2 of the keywords available in the Google Speech Commands dataset. Missed the API key from Edge. So if you go to Edge Impulse, log in, create a project, go to Dashboard, go to Keys, and it should be right there. It's okay if it's truncated. It will copy. It will absolutely copy the API key for you. You're welcome. All right. So we've got this. What's going on here? This script is just a simple Python script, and it is going through each of the Google Speech Commands dataset. It is pulling in each of the files, or it's actually randomly going through and looking for a number of files in there. So like, remember we said 1500 we want. So we've got, so say down, right? Down is a category in the Google Speech Commands dataset. It will randomly pull 1500 files from that and then put them in the down category in the output. During that process, it's also mixing in random snippets of background noise to help let us create a more robust model. It does so for the up directory. Unknown is random samplings from all the other directories, and noise is just random snippets of background noise. These are going to be the 4 categories that we will train a model to recognize. The output does not recognize any of the Google Speech Commands dataset, just the 4 categories that we've provided here. So in this example, it's up, down, unknown, and noise. For the one that I'm going to be training now is going to be house, 0, unknown, and noise. And for you, it's whatever keywords you pick, unknown and noise. Malfunctioning heap of scrap in the available data set. Yeah, I know. That would be quite amusing. Maybe longer than a second, but that would be pretty good. I'm hoping somebody puts other like great quotes in there and train some models to recognize them. I really want to see like makers go nuts with this and like have like light up crazy stuff whenever somebody says like the keyword of the day. Yeah, that would like Pee-wee's Playhouse style, right? I want somebody to say a word and like their house just like starts going crazy. All right. So data augmentation. Why do we do data augmentation? Data augmentation is a extremely useful technique we can do in machine learning that allows us to take a smaller data set and expand it out to a larger data set. And it also helps us create a more robust model. So for like image processing, what we can do is, say we're trying to identify pictures of cats. Well, let's say we start with 30 pictures of cats. That's going to make for a pretty terrible model. What we can do is we can balloon that into like 1,000 pictures of cats by doing things like shifting the cat over, rotating the cat a little bit, and it helps create a little more robust model. To be perfectly honest, 30 pictures is not going to nearly be enough because you're going to identify like one type of cat, or your model's going to overfit that and just identify specifically those pictures and no general cats. The trick in machine learning is just you shove more data at it. That's not always the fix for things, but usually it's like, why isn't my model working? And the first question is, did you give it enough data? So data augmentation helps us create more data from that. And for our case, what we're going to be doing is taking up and putting in background noise. Because we have a lot of starting data, we have over 1,500 and we're going to be creating 1,500 samples for each category. We can actually take a unique keyword or a sample of a keyword and mix in random background noise. And that just helps create a more robust model. If we were going to do real data augmentation, we take each keyword, mix each keyword with a random sample of background data. So each one becomes like 8 or 9 samples. So we start with 2,000 and we end up with like 10,000 samples because each keyword now has different samples with different background. That's even better. We just don't have the time because people would be waiting forever to upload all of that data to Edge Impulse, and the data curation script would take like 3 hours. I did this, so I actually know on my local machine it takes like 3 hours if you do this method to end up with like 20,000 samples. Let's check on the script. How is it going? All right, so for whatever bizarre reason, Colab does not like to show my progress bars. So once it's done mixing, the progress bar will just appear at 100%. The progress bars do work on your local machine if you run it locally. I just never bothered to fix it on Colab. So that's why you're seeing a weird progress bar. All right, so it's finished with background noise and it's currently mixing house. Great, we have time to do some more talking. All right. While that's going, a little bit of history of artificial intelligence. You hear it, artificial intelligence, AI, ML, machine learning, deep learning, all these terms are thrown around and a lot of times interchangeably. And the machine learning community has kind of come up with this concentric model of what AI versus ML means. So if anybody here is familiar and works with ML, I apologize because you've probably already heard this, but for anybody who's new to it, this could be an interesting take and hopefully give you some vocabulary when you're talking about AI or ML. So what is artificial intelligence? It was coined in 1956 by John McCarthy as part of this conference. He wanted to bring people together to discuss, can we make computers behave like humans? Can we give them intelligence? And it was very conceptual, a very small group of researchers doing this kind of work. Later he comes back in an interview and gives a much better definition. AI is the science and engineering of making intelligent machines, especially intelligent computer programs. Okay, John, what is intelligence? Intelligence is the computational part of the ability to achieve goals in the world. So according to John McCarthy here, anything that tries to achieve a goal is considered intelligent. And if we have a computer do that, it's considered artificial intelligence. That is hugely broad. From what I could tell, if I program my thermostat to say, keep the room around 72 degrees Fahrenheit, and it does so with like a few if statements, that's AI. Okay, so AI can be very, very broad. So what about machine learning? So this comes about not much later after John McCarthy. A guy named Arthur Samuel coined the term. If you're familiar with his work, he was famous for making a computer play checkers. And that checkers experiment, I think it took him years to finally get it working. And he wrote a paper about it where he coined this term machine learning. This has more to do with, can a computer learn from experience and apply that experience to data or situations it's never seen before? So that's why he chose checkers, because checkers has a fairly strict rule set. And can you teach it to learn from prior experience to eventually beat you in checkers? Tom Mitchell in his textbook in '97 gave a much more sciencey, specific definition. A computer program is said to learn from experience E with respect to a class of tasks T and performance measure P. If its performance in tasks T as measured by P improves with experience. Basically, does a computer program get better at some task as it's learned from prior experience? So that is machine learning. And we can apply that to things like we can show it a bunch of pictures of cats and have it learn what a cat looks like. Finally, we get to what is this deep learning. So Rena Dechter wrote this paper. Somebody's going to correct me here. I think she was doing biology research when she wrote this paper around in 1986. And she defined it as a class of machine learning algorithms that use multiple layers to progressively extract higher level features from the raw input. Funny enough, Wikipedia of all places gives the best definition that I have found for deep learning. Basically, it's machine learning, but more complex. So like, okay, what are we talking about complex? The idea is that we start to run multiple layers of learning algorithms, where the first one does things like extract features and says, what am I interested in? And that feeds it to the next layer where it may say like, try to classify those features that have been fed to it from the first layer. The reason that's machine learning is because we're not directly adjusting these parameters. We're not directly feeding it these features. We're saying, go ahead and learn. Here's a picture. You tell me what features you want to learn, right? This might be, it picks out, for facial recognition, we might have fed machine learning algorithms originally like, oh, look at where your eyes are or your nose are. And then we feed that to some type of classification to do facial recognition. But this deep learning says, you know what, here's an image of a face, learn it. Or actually, here's 1,000 feature, or here's 1,000 images of faces, learn what those are. And so it goes through and it might pick out like ears and your hairline. You're like, I would have never thought to do that. So the machine's doing stuff that we don't know about. It's outside of our control at this point, or even sometimes under understanding. And that's kind of what makes it this deep learning. We don't know. They become these black boxes. Now, there are ways to dig in and figure out what the machine's looking at with these like heat maps, which is really cool. But we're not telling it, look at these features. The machine's learning to do it. So you end up with this concentric view of AI, ML, and deep learning, where machine learning is a part of AI and deep learning is a part of machine learning. We're using more complex models. So I hope that gives people a broad idea of what we're talking about here. Are there any questions? Well, we're going to go back and we are going to take a look at our script that's running. Excellent. I'm still on 0, so I've got some ways to go. I think everybody in this class, when I ran this last night, it took about 20 minutes. And I'm curious if I'm just talking quickly or if I am. No, I just talked quickly through that. I have no voice. I guess people are trying to ask questions. Yes, I do. I talk quickly. I'm trying to burn through this because I know we only have 2 hours. When I'm making a pre-recorded video, I go a little more slowly and stuff. But for this, whenever I give presentations, it's like, oh, we got to get to all these things. So we're going through these here. So hopefully everybody's on this. Is anybody stuck? I want to ask, is everybody up to here if you're following along? Ooh, we've got some comments rolling in from anybody interested in other data sets. Here is a list. Actually, let's go explore that. That looks really cool. Good. Everybody who wants to follow along is following along and up to this point where they are doing the curation. Shawn will be helping the first-time users of STM IDE. Kind of, I'm going to show you what you need to do in order to run this demo. That is unfortunately one of those things that is a little bit canned at this point. because I don't have time to go into all the features of STM IDE. I've got videos out there that show you like what you need to do to like get to Blinky and all of this. Speak faster, yeah. Okay, so everybody's saying that the curation script is going about the same. So everybody's right about here with the curation. And it has, once it's done with 0, it's got 1 more.
Could you give us kind of a, if we have a minute, an
Mhm.
overview of the tool chain that we're using? Like
Oh,
I'm clicking a lot, but I want to have a better understanding of how everything's linked together.
yeah, very good question. Thank you. So the tool chain that we're using here is, so we're running, I wish I had a slide for this. That's a good question. I didn't think about that beforehand. We have Jupyter Notebook. So on a Google server, we have a Jupyter Notebook that's basically running Python, right? This is all this is just a Python script, more or less. And Jupyter Notebook just lets us run that in, chunks at a time. It's very good for learning if you haven't played with it. I really like it. And so we've got Python running here. What we're doing with this Python is calling, this is the silly part with the Colab, which is why I recommend if you have time, run it locally, because we're running it in Colab. We're actually using Colab here to run system calls, more or less. So like this exclamation point Python, we're actually telling Linux to run Python and do pip to install, use pip to install the sound file package. So sound file is like one library that we're using to read and write WAV files. Later, we'll be using the Edge Impulse CLI. So right now, the best way to think about this is as a Linux box, right? I don't really have a command line into it, so we're using Colab to be a command line. ML ops, I must have missed something. Yeah, I'll get through this question first. We got a few about audio. So that's the first part. And we're using basically strict Python in this curation set. Let's see, what does it install? What does it need? Shutil, Librosa, sound file, NumPy. It's some basic like audio manipulation and NumPy for doing matrix type operations. This Python script, all it's doing is just curation, right? We went through that, we've got curation. So the pipeline from there is once we've curated this data set, we're going to send all of these to Edge Impulse, which is this online tool that does the training for us. And once we get to here, I'll show you what's going on where we're going to do feature extraction to generate MEL frequency cepstral coefficients. Those get fed as features into a convolutional neural network. That's going to be trained using Keras on top of TensorFlow. Once that's done, we're going to download it's going to be converted. The model itself will be converted to a TensorFlow Lite model. We're going to download that and include it in our IDE, our oh good lord, our entire set for STM, for the STM code. That's going to be a library first, just like a C++ library. So I hope that helps. Does that kind of give you an idea of like the technology pipeline we're using here?
Yeah, that was great. Thank you.
Cool. All right, I've got a few other questions here. I got to Blinky last night in STM32, and it was a lot. Yeah, STM32 is like, I now know how to do this in Arduino, and I would have definitely done it in Arduino. STM32 Cube IDE is a lot. It's a professional IDE. It's built on top of Eclipse. I'm not a big fan of Eclipse, but generally STM32 Cube IDE works out of the box. When we gather audio data with hardware, should we use a device or mobile phone? So that is a very good question. The method we're doing with this, with the MEL frequency cepstral coefficients, actually works from just about any hardware recording device, especially considering we've resampled it and we're going to be doing the discrete cosine transform, which then gives us an idea of the overall shape of this spectrogram is kind of what's going on, which means that we can record it with any device. Depending on your machine learning application. So initially when I was trying this, I was trying it without the MFCCs. I was doing it with just the spectrogram. When you do it that way, the microphone definitely plays a much bigger factor into what your sound signature looks like, and you should use just that microphone. So my recommendation is if you were recording data yourself, I would always try to use the same sensor if you can. There are mathematical things you can do to extract features that where it doesn't matter which sensor you're using to a degree. So I hope that answers that question. I programmed a base program, didn't do anything, just looked into the download verified. Cool. We're using Colab as ML ops machine. So yeah, I guess that was the question. Colab is not the ML ops in this case, which is hilarious. It's just a way so that people didn't have to install a whole bunch of Python stuff on their own computer. Yes, Colab is a decent way to do tinkering with ML ops. However, please note that Colab disconnects you from the runtime at 90 minutes if you're not using the mouse or interacting with it. In fact, we may see that happen at some point. In that case, you just click in and get to it. If you've been using it for 12 hours, it will completely shut you down and reset the whole file system, Linux server, and everything for you. So you cannot use Colab to do end-to-end ML ops, especially if you're training like large networks that take a day to train. It's really meant for research. Colab's a great interface for research and training small models, but not for big models, and like not for like setting up a full pipeline. It will just disconnect you. Can we do the edge impulse training locally so we don't have to give our data to somebody else? I do not believe you can at this point, because they're doing all the server, all the training on their side. That would be a question for Edge Impulse. If any of the Edge Impulse people are here, they can answer that one. I know you can set up like programmatic. There's an API where you can set up programmatic stuff, so you can do you can feed it data programmatically, but I still think it has to go through their server. For running locally, that's where I do have training algorithms out there on my GitHub for training stuff locally, but it's not doing the full MFCC thing where you get a better model from Edge Impulse, which is why I'm using Edge Impulse, and it just makes it easier and you can see the graphical flow. Anybody got, oh, here we go. Any got Blinky working with OSX? I've seen some issues with OSX. Whatever you're running, I don't have a Mac, so I'm unable to verify what's going on with Mac stuff. With STM32, yeah, the debugging connection loss shuts down. Other people have run into this. Try using the program from my GitHub to see if that works. There have been other issues with just trying Blinky and where the debugger just shuts down. Can you log multiple channels at audio speeds that are synced? Can you log multiple? This is on YouTube. I'm not quite sure. If you have multiple channels coming in, yeah, right now we're doing mono. So like 16 kilohertz mono. If you've got two channels, that creates another, that creates something else that you would need to train the model with. So you would have to create the entire data set from scratch, because now you have twice the data being fed to the machine learning model. Okay, some people are saying if you're running into problems with the debugger not working in STM32 Cube IDE, go ahead and either try restarting the IDE, restarting your computer, unplugging it, replugging it back in. All the good IT stuff seems to work here and magically fix it sometimes. And done. Good timing. All right. Let's continue running this script. So we've got the Edge Impulse tool done. All this is going to do, actually, let's take a look at this first. So on the left side, you should see keywords curated. Let's go into there and you should see the 4 categories that you picked, or excuse me, the 2 keywords you picked, plus unknown, which is other keywords, and random background noise. Feel free to try downloading one of these. So I'm going to try house. And once again, I don't think my system audio is saved. I'm going to bring this up. So try running a couple of these. What you should hear is somebody saying a keyword from that original data set and mixed in background noise. So give that a shot if you want on your own machine. I don't think you can hear my system audio, so I'll let you guys try that. Finally, run this last cell, and that is going to upload stuff to Edge Impulse using that API key that we gave it. So I'm going to sit here and let it start going. Yay, it's uploading everything. If I come into here in Edge Impulse, I go over to data acquisition, and you'll start seeing some of the data roll in. It may not be in real time. You might have to refresh some stuff, but it should happen. In fact, I think it does test first. Yes, it does test data first, which brings up a good point. Why are we splitting stuff into test and training sets? So we're running that script while it's uploading for everybody. What we're doing here, and let me get rid of my downloads. What we're doing here is we're splitting the data set. So we've got 1,500 samples, and 20% of those are going off to this test set, which exists separately from this training set. The samples were randomized when they were chosen from the Google Speech Commands data set. So when they were given those file names of like 0.0000, 0.0001, 0.0002, those have been randomized anyway. That's why I didn't use like a hash or anything. They've already been randomized. And that's why the naming doesn't particularly matter for those individual keywords. So we set aside 20% for testing, and the rest of it's going to be used for training our neural network. So why do we set aside stuff for testing? Well, we set aside these keywords for testing because we need a way to verify that the model worked. Okay, that seems simple enough, but we absolutely do not want to test with any of the data that we used for training. And the reason for that is because what you'll find often is that your model, usually when you start, the model itself will overfit the data. And that just means that the model is very, very good at picking out the specific instances and samples that you've given it, and it knows how to identify those. And it's very bad at generalizing to data it's never seen before. So when you go to deploy it, if all you've ever done is looked at training data, and you go to deploy this, and you're like, why isn't it working? Like, well, you probably overfit, or you probably had the model overfit the data. And so the test set helps us determine if that's been overfit, because it's data that's never been seen by this model before. So it's very, very useful. I would say you always want to have a test set. Is it 20%? Is it 10%? That can be up to you, whatever your needs are. But in the machine learning world, 20% set aside for testing is kind of your normal. And let's see how that's going. This is still rolling. So let's talk about features and what's going to be going on here with features. So the first step, once we've uploaded all of the data to Edge Impulse, we're going to be extracting features. Features for us are going to be the MEL frequency cepstral coefficients. Yay, whatever the heck those are. I'm going to briefly run through this and then give you a link to a site to go read on your own if you really want to scramble your brain for what these are. So here we go. MEL frequency cepstral coefficients. What we're doing is, here's our sample. Here's an audio sample of somebody saying like 0 or something, right? We're going to take a window. We're going to take a slice of this, and we're going to compute the fast Fourier transform, which gives us basically our power over our frequency. So we've got these bins, right? So like at 0 hertz, there's this much power in this spectrum. And at 4,000 hertz, we've got this much power in the spectrum. And it kind of looks like that. And it's no longer a time series. We're not working in the time domain anymore. We're looking at it from a frequency. I wish I had time to get into how Fourier transforms work, but one, I forgot most of my signals and systems class, and two, we don't have that kind of time. That is a fun class if you ever want to get into how Fourier transforms work and doing them by hand. Anyway, the next step we're going to be doing is we're going to be taking the MEL-spaced filter bank. MEL spacing is basically taking a linear set of filters for lower frequencies and logarithmic filters for higher frequencies, and then combining the energy that it sees in each of those frequencies and basically adding it up to create a set of numbers, an array. So this 0.002 comes from this first filter, where it just takes the energy that it sees here, sums it up. That's the first number. The second one is the second filter. You notice they overlap a little bit. So it adds up all the little blue line, all this power, all these power numbers. You get an energy, and it ends up in the second one, and it continues on. The reason they're specific in MEL space is because MEL spacing has to do with how humans perceive sound. We don't perceive sound in a linear fashion. In fact, humans don't actually perceive sound in a time sequence like this either. We don't process, individual little samples here over a series of time. Our ears have these hairs that resonate with various frequencies. So how we hear is actually closer to something like a spectrogram. And how those individual hairs are vibrating has to do with the frequency that they're basically tuned for, essentially. But though that tuning happens to be more linear in lower frequencies and more logarithmic in higher frequencies. So this replicates how humans hear. Obviously, if you're going to do another animal, this would look a little different, but we're trying to go for humans here, right? We're using human speech. Once we have this array that, remember, comes from this little window slice, we then compute the logarithm, I think it's base 10 for this, of each of these numbers. And then, so we got this array, and it's just, oops. So we've got this array, and it's just, you know, the logarithm of each of these numbers. From there, we compute the discrete cosine transform. And what that's doing is it's basically like another Fourier transform, more or less, but I believe you're using real values instead of complex values, if I remember how the DCT works. And this helps us give an idea of what the shape of the original Fourier transform looked like, or the FFT rather. And by shape, I mean how many, like what frequency of things you're going to see. So it's kind of like taking the FFT of the FFT in a bizarre world. Like, think about it that way. And that's kind of where I gave up on really trying to understand what's going on with MFCCs. But my basic understanding is that you've got the lower values kind of give you an overall shape of your Fourier transform, and then the higher values give you information about what some of those peaks look like. And then so we just move that window over our entire audio sample, and we drop in each of these arrays, the MFCCs, over this whole sequence. So we take the first one, that becomes this first set of arrays, we slide the window over, we compute the MFCCs, that becomes the second one, and so forth until we get to the end of the audio sample. Another way to think about this is how we're doing training. When we get to actually computing this in real time, these are being performed basically in real time. So as the audio streams in, it's taking these MFCCs, and every time it computes a full section of MFCCs, it then tries to classify that and just sending that off to the neural network for inference. So we've got the MFCCs, it's just a two-dimensional array. That's all it is. So we get this two-dimensional array, and it looks like an image, which means we can actually use neural networks that are better at image classification or meant for image classification to classify audio, because these look like images. And here's an example of stop. Here's an example of zero. Even though they happen at different times, you can kind of see that the bands of the MFCCs look a little different. And that's what we're training this neural network to do. Okay, so you got through all this and you're like, what was he just talking about? Oh my goodness. Don't think about it too hard. Like I said, my brain started to hurt after getting to that like DCT step and going, okay, I kind of understand what's going on in the DCT, but I don't understand why we're doing the DCT of this like logarithmic stuff. There's a great article on practical cryptography if you want to go read more about it. Just know that MFCCs for features are very popular in things like automatic speech recognition, which is what we're doing. All right, I hope that helps. Let's go check on our uploads. They are still going, but we are, let's see, 0. So many, noise, 0. I think it still needs to do house. So this is still going. And we can stop here and see if anybody has questions. I'm gonna have to scroll all the way down, so I apologize if I've missed stuff. So we're image classifying the spectrograms or the numerical values of the arrays. Very good question. We're basically classifying the spectrograms, but instead of spectrograms, they're the MFCCs. I originally played with this by classifying spectrograms. It works. It saves you from having to do that DCT, that discrete cosine transform step, which requires a lot of, in fact, that requires more computational power than the actual neural network, which you will see in a minute, which is kind of crazy. But you can classify the spectrograms as images. And those images are just two-dimensional arrays. They're grayscale images is all they are. I know I showed you ones with color. They're grayscale images. Is the input assumed to be exactly 1 second long? Yes, the MFCCs are going to create basically something that looks like this. And in order to get exactly, I think it's like 16 MFCCs, at least in this example. I don't remember what it's going to be in edge impulse, but in order to get that exact number, it needs to be exactly 1 second long. So yes. how do we figure out when to start the sample for classification? If we're talking about deployment, what it's doing is it's doing this in real time. So every time a new chunk of audio, so like let's say this window of audio is 100 milliseconds. I forget exactly what that number is, but let's say this window is 100 milliseconds. Every time a buffer fills up with exactly 100 milliseconds, it takes that, performs the MFCCs or calculates the MFCCs, so you get this array, and then you fill up another buffer that looks like this, and you just start queuing these. So it just like continues to queue these, and as you get past a second, it starts dropping the first ones off. So you've got this moving buffer of MFCCs, and then every time you get, let's say, what do we say, 16? So every time you get to like 6 or 7, like every time you add 6 or 7 new MFCCs to the front of this, that gets sent to the inference engine. Which then performs the classification. So the moving buffer overlap, yes, the moving buffer overlaps. So new samples will come into this every time you add 6 new here and drop 6, even though it contained ones from the previous sample that, or the previous buffer that we tried to perform inference with, we send that to the inference engine. So on the Arduino, that's like every 333 milliseconds. On the STM32, we can actually do that every 250 milliseconds. Yes, it is exactly a slide. It actually ends up becoming like, it's not a sliding window, it's a sliding window. Yeah. The sliding window analogy, or the sliding window, works better when you think about it taking samples in training. When we're doing inference on the microcontroller, it's easier to think about it as it's just constantly reading audio in and then updating a buffer, kind of like a queue. And then every time that queue gets to a certain point, or you've added X new queue chunks to it, that goes to the inference engine. But yeah, like a sliding window. And this thing is still going. All right. Yeah, you're welcome. Is the input assumed to be exactly 1 second long? Yes, we answered that. Sorry, I just answered that one. So we're image classifying. Yep, I got to that one. Sorry, I'm going backwards through the questions here to see if I can get to any, because we're almost done with this. Coming from music background, I would highly recommend Julia Smith's work on the DFT. Awesome, thank you for that link. Is this process run on each sample or on a collection of samples, where a sample refers to a single audio file? Thank you, that is a good question, because I often get confused when we start talking about sampling audio, where you're taking an individual value at like 16 kilohertz, or a sample for machine learning sense. And a sample, when we start talking about machine learning, is a 1 second audio clip. And we're going to be sending those samples to for training. I hope that helps and answers that question. That's the one class I failed. You must be talking about signals and systems. Yeah, I enjoyed it, because I actually enjoyed had this weird thing where I enjoyed doing the Fourier transform by hand. It's like, oh, I just performed these steps. I was way better at that stuff than like the math class, where you're like, oh, figure out the permutations of people sitting around a table. Like, I was terrible at that math class, but I could do the Fourier transform by hand. I always thought that was really weird. And I enjoyed signals and systems. It's just like over time, I just forget some of the nitty gritty details of it. Another recommendation for Zach Starr and 3B1B. I guess is that the 3 blue 1 brown, or 3 brown 1 blue? That I always mix those two up, but that's a great YouTube. They have really good stuff about like Fourier transforms, convolutional neural networks. Their stuff's really good. Definitely recommend checking them out. I failed that when it became an electrical and an industrial engineer instead of electrical. And yeah, that is, unfortunately, signals and systems ends up kind of being the weed out class for a lot of people. For me, it was junior year. Somebody linked in the practical cryptography for MFCCs. Yes, that is the one. Thank you for posting that in the chat. That article really helped me get an understanding of what's going on. It's still quite confusing. And thankfully, there's a number of tools out there that just kind of do them for you. All right, while this is still going, let's start talking about, I'm going to go check on this after we look at training a neural network. So the fun part is once we get to the actual training step, it goes a lot faster than this. The joke in the machine learning world is that you will spend 80% of your time manipulating and massaging data and 20% of your time on actual machine learning. Backpropagation, yes, more or less we are doing backpropagation. I don't remember the exact algorithm we're going to be doing for training, but yeah, it's essentially backpropagation. Edge impulse, it's like click button, magic things happen, but I'll show you where you can manipulate Keras code if you want to create your own neural network. But we won't be going into like, picking out your learning. You can pick out your learning rates, but picking out like measurement values and things like that. So training a neural network. So we're going to be using a convolutional neural network. In Edge Impulse, they recommend a one-dimensional one, which essentially just takes, so we've got that image, right? We're thinking about the spectrogram or the collection of MFCCs as an image. And essentially what that's going to do is it's going to take a filter and just slide it across. And you'll have to forgive me, I don't remember if it's time-wise or if it's over the values. I will have to look at that one later, but it's going to slide this one-dimensional filter across it. That's the first layer. Then we get to max pooling. All that does is just looks at individual in this filter and says, okay, what are my max values after this filter has happened? And then just gives us those. I'm in NLP, and interestingly enough, we're using filters and other convolutions to parse tokens and recognize grammar. Oh, interesting. Yeah, I don't know much about NLP, so that's fascinating. I'm not surprised that it's very similar of this idea of like filtering and convolutions, and like those things definitely overlap. And a lot of this convolution stuff came from vision processing of filtering images prior to machine learning, and by basically saying we're going to make these filters work and have the machine just figure out what filters it needs, what values in these filters. So that's just the machine learning part of this. We're going to actually do that filter and pick out the max values twice. So that kind of like takes this image and squishes it down to its raw values. And the idea is we're trying to get our features from that image, right? We've already extracted the MFCC features, and now we want to have this convolutional neural network say, what are the features in this image that I care about? And so we're going to take those, we're going to like process this down to like the individual like pixels that it cares about. And by individual, I mean, there's still going to be a few dozen pixels that it's going to care about, and maybe 100. It's going to flatten that all to a one-dimensional array, and then it's going to send each of these to a node in what's called a dense neural network. It's just one layer. In fact, it's just 4 nodes that correspond to each of our classes. And the softmax, the output of each of those feeds into the softmax function, where softmax gives us basically a set of probabilities that it thinks the neural network heard one of the classes. And these probabilities after the softmax layer should add up to 1. So if it thinks it heard the word up, it comes through this neural network and it spits out up like 0.9, and then the rest of these like less than 0.9, but they should all add up to 1. And then all we need to do in our code is say which of these outputs is the greatest in order to determine what it thinks the neural network picked as the class. So that's what's going on here. And yes, we are going to be using essentially backprop, and we're going to be using a tool that you just click it, and I'll show you where you can modify some of the hyperparameters if you wish, if you're into machine learning, and give you some recommendations as to where you go to learn more about that. Look at this. What is he talking about? If this is all new to you, I highly recommend Andrew Ng's class on Coursera. I took that about a year ago, and it was by far the best introduction to machine learning. It takes us, I think, a couple of months to get through, where you're doing about 5 hours of work each week. And you start with like matrix algebra, and by the end of it, you have an understanding of what machine learning is, and you basically design your own very simple neural network in MATLAB is what you're doing. And that helped tremendously. And then from there, it's like a bunch of books and things you can just like, how do I learn Keras? How do I make bigger neural networks? What's new in industry with this? And we're playing with things right here that are like, like a dozen or less layers, and you get to industry and you start looking like, oh, how are they doing object detection for vision? And you're like, oh my God, that's like 300 layers. How do people come up with this? And you're like, oh, this is how people get PhDs. So, or this is how Microsoft makes money by developing these neural networks. All right, this is still going. Cool. I want to keep checking on this, but Once we get there, we're going to evaluate on the test set. And I want to wait to get there to do that. But in the meantime, if everybody wants to go ahead and start putting this together, make sure you've got your headers soldered on your microphone, connect it to your Nucleo board. We've got the left-right clock. So that's just a clock signal that toggles back and forth. That's how you get 2 channels out of these. That goes to A2. You've got your data out, that goes to D4. Your bit clock, that's the really fast clock, that goes to D3. And you've got power ground. Make sure it's 3 volts, not 5 volts. Select line, that determines if it's left. That determines if this microphone is left or right channel. I think it defaults left. This board has this line pulled down to ground, so you don't need to put anything on this line. And I think it defaults to the left, and my code just handles that. Like the demo code that we're going to use just handles that for us. Are we done? Ah, we're done. Good timing. Okay, this took a little longer than when I tried this yesterday. I think it's because everybody's trying to upload data to Edge Impulse right now. Where is? Well, I had a chat bar up, so I was being able to watch some of that. So we should have data all in Edge Impulse right now. Hopefully everybody's about up to here. Check it, make sure you've got, am I in test data? Yeah, here we go. So your training data, you should have about 20 minutes of samples in each of your categories. 0, house, noise, unknown. And if you go to test data, you should have about 20% of your total data. So that's about 5 minutes of each. That's like 25 minutes of each one, of each class. Let's go to our impulse design. This is the pipeline. This is your ML ops, basically, from a graphical perspective. This is where you can adjust your window size, how much they hop. We're going to keep everything at a second. There's no really windowing going on here because it's just one 1-second chunk of data. Click to add a processing block. Edge Impulse recommends that we use MFCCs, which we just talked about. Let's add that. This is just feature extraction. This block converts those audio files to the MFCCs. Add the learning block. They recommend Keras, great, or a basic neural network that's been developed in Keras, great. And what I can't see because I've got that window over there is Save Impulse. So make sure you click that. That is hugely important. And then you should see these blocks appear on your left side. So underneath Impulse Design, you should see MFCCs. Feel free to play these. You can actually go through and view your different samples. And you can play those. And you can actually see what your coefficients look like, what these images are going to look like that are going to be features. What we need to do is actually convert all of them to features. So click on Generate Features, and then click Generate Features. And once again, we wait for a couple of minutes. Welcome to the world of machine learning. The XKCD joke about the programmers fighting on the chairs. It's like, get back to work. Oh, we're compiling, that kind of thing. In the machine learning world, it's, oh, I'm training, or I'm, extracting features. Like you sit around and you wait for this stuff to happen. And what I've noticed a lot of times with machine learning, with the exception of diving really deep into the math of what's going on into each one, it's often considered very black boxy. If you've ever done any like RF work, where you have these tools and you're like, oh, I want to design a dipole or whatever it is, and you're like, I'm going to tweak it in this kind of way, and you just run the simulation. You come back in 3 hours and you're like, oh, well, that didn't work, and you're like, bend it a little bit in the simulator. You're like, run it again and come back. So that's kind of what happens in the machine learning world. You start with an idea, maybe you look at a research paper, and you're like, oh, this model performed well for this task. I'm going to start with that model, and then you start tweaking some of the maybe you like add an extra layer, or you insert some nodes. You're like, you know what, let's try a one-dimensional CNN instead of a two-dimensional CNN and see how that performs. And you just kind of like test it and go and iterate and iterate and iterate until you get to something that works best for your needs. Because a lot of times what you'll find in machine learning is that it's not about it works 100% of the time. It's one of those, 60% of the time it works 100% of the time, right? You'll find that it misses data or it triggers on the wrong thing. So if anybody was there last night for the Bring a Hack, my trick or treat thing definitely picks up chicken feet. That's Mr. JP over at Adafruit gave me that one. It's like chicken feet. Oh, it picks up. That's a false positive. So what that means is like I need to go collect a bunch of data. If somebody's going to be commonly saying chicken feet around me, then, or around the device, then I need to make sure it's trained to not respond to that. So one thing you might need to do is then collect a bunch of data that says people saying chicken feet, and either that as a separate category, or it's part of the unknowns now, and a lot of the unknowns, so that it's close enough, but it knows that that is not the correct word, and it starts to pick up features in that utterance that it knows is not trick or treat. Feel free to look at the feature explorer. I'm honestly not sure what's being combined here, because each sample should be a full image. Trying to see where that is, and I can get you the exact number of. I don't have a number of coefficients, so there should be 32 in each time slice. Number of filters in the filter bank. Yeah, I'm not quite seeing it. So it's like 13 by like 40 something, I think. So actually, when we consider dimensions going into the neural network, this is actually like a 1,000 dimension input, which makes it a little conceptually hard. Another way to visualize this, or another way to think about this, is when you start looking at things like this. When you see your dots pointed out to like, oh, machine learning is all about finding the boundary and grouping these together, and like, oh, is this one class? Is the orange one class? Can we define a boundary, a mathematical boundary that separates these classes for us? That's what's going on. It's just that humans, we stop being able to really comprehend stuff after about 3 dimensions. It becomes difficult, and we start talking like 1,000 dimensions, like it's really tough for humans to visualize that. So think like, if you think accelerometer data, right? I'm going to capture accelerometer data and like X, Y, Z, and maybe those get clustered together, and we can create a machine learning algorithm that, you know, identifies different types of positions or different types of vibration. And it's a little easier to deal with something like that. But since we're dealing with audio, we've got many more dimensions going into our neural network here. So we're done with generating features. Let's go to neural network classifier. You know, all this talk, we spent like what, like an hour, almost an hour and a half talking about extracting features, and training the neural network is going to be like the easiest thing in this entire demo. That's the funny part of this whole thing. But I want to get to the deployment side, running it on our microcontroller. Keep all of the defaults. I'm going to tell you that right now, and click start training. So while it's going, I can kind of show you what's going on here. Number of training cycles. Somebody mentioned back propagation. And you'll have to forgive me because I lost my chat window. I was able to keep up with chat. Aha, here it is. Okay, go to impulse design. After upload, go to, okay, somebody's asked. Can we go over the impulse steps again? Mine just finished. Yeah, let me briefly do that while this is training. So we go to impulse design. You want to add the blocks here. You want to add, it's going to recommend them for you because it knows it's audio data. So add the audio MFCC one, add the Keras block, the neural network that's been done in Keras, and then you want to click save impulse over here. That will give us new blocks on the left side. Click on MFCCs or MFCC, click generate features, click generate features, and wait for those features to be done generating. So now we have a big array of MFCCs on the server. That's what's going to be used to train the neural network, not the actual audio data. And then go to your neural network classifier and click the train button or start training. That's where we are. All right, that was a good question. Since as people are finishing up there, but that way mine can stay a little ahead here as I'm blabbing. So number of training cycles. So each epoch is what we're calling it here. Takes some of the training data. Remember, this collection of MFCCs. It sends it through the neural network. So that would be your forward pass. It comes out with basically your probabilities of which class it thinks it is. And it's going to be all over the place when it first starts, because all these parameters, these numbers inside this model are randomized. And then it's going to say, hey, how close were these probabilities to the actual label? If we sent it up or house or 0, is that what was predicted? And there's a loss. There's a loss function that happens that says how it kind of measures the distance mathematically between how close it thinks it was to the original label. And then the whole idea of this back propagation and this training is it tries to minimize that loss. So it updates, it goes backwards through the neural network, and it updates these parameters based on this back propagation algorithm to try to make that loss smaller, or more or less the output predictions closer to the original label. If it thinks it's 0, then it should be like 1.0 like probability of being 0 and 0 for all the rest. And if it's not that, it goes back through and updates these update these parameters, these numbers inside this neural network. It's an iterative process. For a neural network like this can take a little bit of time. For some larger networks, this can take hours or days. The GitHub says we need to add data acquisition, upload data in EI. So if there's two tracks in that. If you're looking at the GitHub write-up, there's 2 tracks. One track is you're doing everything locally, where you're doing curation locally, and then what you do is you go to Edge Impulse. If you've done it all locally, you need to go to Edge Impulse, and there's a button here that says upload existing data, and it basically just gives you a computer interface that just uploads all the wave files from your computer if you did it locally. If you're doing everything in Colab, it's using the command line tool to just automatically send stuff to Edge Impulse. Waiting for the job to be scheduled. I wonder if the Edge Impulse guys are sitting there going, oh, what's going on right now? Yeah, I think we're DDoSing EI. I'm gonna have to chat with them and be like, hey, did you guys notice an uptick of all your servers? What went on? Oh, no, that's good. All right, so hopefully we are done. I really hope we're done. Okay, so it looks like I lost my output here. And I don't want to retrain because I actually have everything going on here. So in yours, you should see something that says loss, accuracy, validation, loss, validation, accuracy. And during the training sets, they pull out a small test set that get integrated back into the training set, and they hold those aside for a second, do one pass basically of your forward and back propagation, and then they test the model with that validation set, and then those get mixed in and randomized for the next epoch. Basically, is my understanding how they're doing it for this validation set, because normally when I've done it, I've pulled aside a validation set to use separately. Do we leave the neural network settings as their defaults before we click start training? Yes, please leave them as their defaults. Give me just a second, I'll go through a couple of those. But this is where it's like, go learn a bunch about machine learning, take Andrew Ng's class. You'll understand more about what these are usually called hyperparameters. You'll understand more about what these hyperparameters do. And you can feel more confident in manipulating these to serve your purposes. But for now, just keep it as default. What you should see, if you scroll all the way up to your original first epoch of that training pass, you should actually see that loss start to go down, and you should see your accuracy go up, both for the regular, your training set, as well as the validation set. If your training set starts to split and become more accurate than your validation set, it usually means your model's overfitting. That means it's better at predicting just things it sees in the training set and cannot generalize to things it has not seen before. And we're going to test that with the testing data. So for these, quick question about these, this says how many steps does it do? Anything between 30 and 100 seems to work for this, but you can actually manipulate this and do what's called early stopping. You can change this to 30 if you see a lot of overfitting, and have the model stop a little earlier to kind of like don't try to learn more, because then you're going to start overfitting to that data. Learning rate, there's pros and cons to higher and lower learning rate, and minimum confidence rating doesn't really apply to us. It only applies to when it gives us testing here, but we're going to get the raw probability scores out anyway when we go to the microcontroller. Do the data set duration of clips, should they be the same? Yes, the data you send to Edge Impulse, I believe, and the EI people can correct me if I'm wrong here, but I believe they all need to be a second, or at least they could be 1 second, 2 seconds. They all need to be the same. My script actually truncates anything over a second, or it pads zeros to make it a second. So if you're using my curation script, it accounts for that. Just make sure where the utterance isn't going to be truncated. Yes, start training if you've not done so. This output refreshed for me. So what you should see is like a bunch of output here. And you should see a confusion matrix when it's done down here. Save for machine data. I'm not quite sure what you mean by machine data. Do the data set duration of clips should be the same. So they generally should, otherwise you're gonna end up with different lengths of MFCCs. Machine sound data. So like sounds from a machine, or like when you record? Sorry, I'm not quite following that question. Okay, so sounds from a machine. Yeah, I guess they should all be the same. They should be the same duration. Because otherwise, like you have to remember that your neural network expects exactly a number of inputs. So like that image that is a like 13 by 40 whatever image, it expects like exactly that array as an input. If you don't feed it exactly that, you start throwing a whole bunch of errors. Okay, so confusion matrix, you have your, let's see, actual label unknown. So you've got your actual labels on this side and your predicted labels on this side. What you should see is the numbers in the diagonal should be the highest. And that means it's doing a decent job of predicting, and it's got an 80% accuracy. I don't see any neural network classifier on my EI. It should be on the left side. I've done this before. Don't forget to click Save Impulse after you've added them over here, and that should cause them to appear over here. Yeah, if you don't click Save Impulse, they don't show up over here. Say 15-second clip to 15 clips of 1 second. Yes, if you're creating your own samples, they need to be 15 clips of 1 second each. Each of those is what we're feeding into Edge Impulse. All right, so you can do live classification. No, not live. Sorry. That is if you actually have a microphone connected and it can read it. We want to do model testing. That's actually going to take this is our test set, the 20% we set aside. So click the top to highlight all of those, click classify selected. You'll see what it's going to do here is it's going to take each of these samples that we set aside a while ago, and it's going to send all of those through the neural network to classify that for us. I don't see anything that says save impulse. So if you go to impulse design, and you should see audio MFCCs. So if I modify this, actually I can't modify because it's going to wreck everything past it. So if you see this here, like I don't see it, it should be over here on the right side underneath output features. What tool to recommend cutting the clip? Audacity. No worries. Audacity is definitely the tool you should use to cut the clips. If you find a way to automate them, great. But because you can't be quite sure where that utterance is, like you could create something that says, oh, I see the utterance starting, and then you can try to like center it or move it around, and then you can come up with some automated tool to truncate exactly a second or crop out exactly a second for you. But because I was working with at most 100 samples, I was just doing everything on Audacity for the custom stuff. All right, testing should be done. We can come back to here, and it did not work for me. Let's try that again. Testing is at 65%. Awesome. Some other people's testing has rolled in. What is mine at? 73%. Oh, mine was better than last night. So this is a case of overfitting. Most of the time you will find that it overfits. Mine actually like performed surprisingly well. I got like 65% last night. This is a general case because we trained too long, the model's not quite right. For whatever reason, it overfit that data, and now it's not as good as classifying unseen data. There are a number of techniques you can do to combat this. One of them is to stop it early. If you want to, I recommend going back and try training with 30 epochs instead of 100. The other thing is getting more data. You can always get more data. You can try adding in different layers in the neural network. So if we go to the neural network classifier, you can actually add new layers. You can try, if you know what you're doing with neural networks, you can try adding different layers. You can try modifying like your dropout rates, maybe try 0.5 dropout rate, right? Like dropout is great for preventing over 15-minute warning. Oh shoot, I thought we were going to 6:15. We're going to do this faster. All right, let's go to deployment. Can you add Keras early? I don't think you can. So in deployment, we're going to go to actually C++ library. Feel free to analyze if you want, but I'm just going to say go ahead and build. This will tell you, this will give you an idea of how much time it's going to take and what kind of processing you'll need. Note it's not giving you the MFCC calculation time. So with that, and I apologize, I'm going to have to go a little more quickly here. Go back to the GitHub repo, download the code. So we should have, so once you've clicked build for Edge Impulse, you've clicked build, go to the GitHub repo where the worksheet is and download that zip. So you should have 2. And of course, Windows is showing me that. So speech recognition, unzip both of these. Note that if you are on Windows, you will want 7-zip. You will probably run into Windows running out of space to print out its file names or its file paths. So yes, I'm going to use 7-zip to extract this. I'm going to use 7-zip to extract both of these. Intrinsics for single instruction, multiple data. I don't believe it does because I don't believe these ARM microcontrollers are set up for that. So you should have, so this is our model that we downloaded from Edge Impulse. This is what the library looks like. Our model is actually in TF Lite model. You need to click the build button at the very bottom for Edge Impulse to get it to build and download for you. And that just takes the model that we created, we just trained, basically compresses it into a TensorFlow Lite model, builds a library around it, and downloads it for us. So what we need to do is go into the EI keyword spotting master, or not go into there yet. That's what we're going to bring in as our demo project. So open up STM32 Cube IDE, launch that. Oh, end time is 6:15 minutes. Okay, so just to confirm, we've got like 25 minutes, right? Awesome, thank you. Whew, I was gonna like start burning really fast here. Okay, so STM32 Cube IDE, bring that up. What we want to do is file, import, and we are going to import. This is where actually I forget. So this is why I wrote this all down. So in this GitHub, go check out the embedded demos. Go to the L476 one. There is a walkthrough. This is where we are now, is in this second walkthrough, because it's going to, when I give more examples into this, when I put more examples in this GitHub repo, I'm hoping to flesh out each one and like, how do you make this example work? This shows you your connections. And what looks like we need to do is file import existing projects into workspace. This is the step that I always mess up. So click on existing projects into workspace. And this is where Eclipse does its, I try to make everything a GUI. Copy projects into workspace, make sure that's all selected. Copy projects into workspace, we want that. Yeah, that looks good. Finish. Okay, so for anybody who missed it, download my GitHub repo, the one where the worksheet is, download the whole thing. And you'll also want to download the Edge Impulse model that we created. So if you go to deployment, there's a build button at the bottom. That's what downloads everything. So you want to select C++ library is what we're using, and then click build. So back in STM32, so we've got the project. So this is from my GitHub repo. Once again, I have to go to the worksheet now because I don't remember these exact steps. Projects Explorer, so we need to delete the model parameters in TF Lite directories. So this demo comes with a pre-trained model, and that pre-trained model exists in the TF model, as well as some information about it in the parameters folders. So in EI keyword spotting, delete that one. Yeah, you can delete that from the whole file system, and delete TF model, TF light model. There we go. File import general file system. So here is one of the weird Eclipse things. When you're working in Eclipse, you've got the projects over here. So I've got a few projects going on. Make sure you click on that project when you're working in it, or bring up something like core source main.cpp to make sure you're working in there. Otherwise, if you accidentally click one of these and you go to import a file, it's going to import it into another project. So always make sure you've got the project you're working on selected, or feel free to close these wherever the close is, their close project. Feel free to do that, and it makes it a little neater. And it's a little harder to mess up some of these steps. So click on that, file, import, general file system. So general file system, next. We want to select the model parameters directory. How do we open the project in Cube IDE? So we're on this walkthrough right now in where the GitHub repo where my original worksheet was. If you go to embedded demos, STM32 Cube IDE, keyword spotting, the Nucleo-L476 keyword spotting, the walkthrough continues for this specific microcontroller. And this gives you the exact steps you need to perform to get the stuff to import. I hope that helps, because I can't go back and like show you this step again. So we need to import, where was I? The model parameters directory from the model we downloaded, because we're replacing the model that was in there. That is the speech recognition 02. So the model parameters, select that folder. It should look something like this. We gotta select them, get a create top level directory. Yep, that looks good. Finish. Okay, so that should have dropped. Oh, I messed that one up. So I put it in here. That's where I messed up. So delete that. The ID is putting my CPU. I don't know. Sometimes it can do that. If it's the first time you're doing, if it's the first time you're running the IDE, it might hose your machine for a while. We do not record data using the microphone. How will the model work? It's all because of how we did it with because the MFCCs, the MFCCs are what the key here is. It allows us to record with different microphones, create a model, and then it listens from whatever microphone we want. So let's try this again. File, import. My love of Eclipse is showing. Download model parameters, select folder. Here we go. So into folder, it needs to go into EI keyword spotting. So if you've selected this, it should go in here. Otherwise, you can click browse. Make sure it goes into EI keyword spotting. It's very important that our model exists in this directory because of how I have the include set up. So there we go. Model parameters is now inside of there. We need to do the same thing with the TF Lite model directory. So we actually want to, if you select this, it helps. I'll try it from here. File, import, file system. So let's do the TF Lite model. Select those. So you see it tries to put it in the base project directory. So I'm going to go browse. Here's my project, EI keyword spotting. Select, create top level directory is selected, and finish. Okay, so the three directories. So we've now started with basically my template demo project. We've replaced the model with the one that we trained from Edge Impulse. All right, project build configurations, set active releases. Oh, here we go. Project build configurations, set active. It wants to default to debug. We actually need to go to release. The reason for that is because there is a compiler flag that gets set if we use debug that makes everything run really slowly with TensorFlow Lite. So we want to make sure we're doing release here. If you want to debug stuff, go for it. I don't recommend using this program to debug TensorFlow Lite because you'll overflow your audio buffer. It's very, very narrow margins when it's trying to fill up an audio buffer and then run your inference. Okay, so now we want to new configuration and then build the project. Project, build project. And then this is going to take a little bit because not only does this have to compile what we have going on, this has to compile the model and all the edge impulse stuff as well. While that's going on, I can show you a little bit in main. So unfortunately, if you've never done STM32 cube stuff with their HAL and in this IDE, this is going to be a little confusing. Like I said, next time I do this workshop, I'm going to do it in Arduino because I think most people taking this workshop have had some hopefully experience with Arduino. It would be a lot easier. Lesson learned. I would do this in Arduino in the future. That being said, I like STM32. I can do a lot of stuff with it on a low level, even though I'm using HAL, which is like somewhere between like reading and writing registers in your Arduino framework. So what's the big stuff that we need to care about is here's main, here's your entry point. And there's stuff here that sets up HAL is STM32 stuff. That's setting up all of your peripherals, your clocks, your timers. Even if you yes, Kai, you're correct. Even if you use HAL, you still need to read the reference manual. That is so very true. It just does some stuff that makes it a little easier, but then eventually you get to the point where you're like, wait, HAL doesn't do this exact thing I want. And then you have to go like to a lower level library or doing manual register reads and writes from there. EIPrintf, they have us implement EIPrintf. If you scroll down, you'll find that function. I have Control F. So here it is. All it's really doing is calling this, which just uses HAL transmit. So that's coming out over the second UART port. That allows some of the edge impulse stuff to spit out over UART that helps us debug. That's all that's going on. So back in loop, oops, sorry. Yeah, loop, right. We're in Arduino. I'm already thinking Arduino. That'll print out some stuff. It's then edge impulse sets up all of our buffers and sets up the TensorFlow Lite stuff. And then in here, this is where the juicy bits happen. This waits for the audio buffer that records exactly 250 milliseconds of audio data to fill up before returning control. If you let that overflow, it kind of breaks this whole process. So if you put a bunch of code here that then prevents it from, that overflows that buffer because you waited too long at 250 milliseconds, you'll break the whole process. So that's why you have to be really careful here. It will do classification. The magical thing is we take that raw signal, that raw audio data, and then we send it, we call run classifier continuous with it, and that performs the MFCC extraction from that, and then does inference with the neural network that we trained. We then print the output. Oh, I thought I updated this from last night. I thought I pushed this. Oh, well, this will still work. I'm gonna have to go check that. I thought I pushed it. So when you're putting your code here, it should actually be outside of this print statement. I'll make sure to update the GitHub repo. I thought I updated that last night. Anyway, it should still work. So we need to go to run configurations. Oops, wrong one. Run configurations, select application. Okay, run configurations. You should see something like this. And why are you not giving me a new configuration? Press the new configuration button. Oh, that is awesome. Do we have an ELF file? Releases. Yes, we have an ELF file. Why is this not working for me right now? Okay, yeah. If this is the first time you're using L476, the only thing that helped was connect to the board of Arduino, program Blinky. Yeah, there's some weird stuff that happens with that debugger connection. So somebody's getting stuff. Yay! Awesome. And funny enough, this debug connection thing is not working for me right now. Wonder if I open these projects, will it give me something? This is more Eclipse not doing what I want. Oh. I need to click on, oh, there we go. I need to click on the C++ application in order to create a new configuration. Of course, why didn't I think of that? So we create a new configuration here. It should point to the ELF file we just compiled, which is what we're going to send to the board. Make sure it's release. That should be our configuration. Otherwise, debugger doesn't really work. And that should be it. So we're going to click run. It should have been built. You shouldn't see compile errors with this. You'll see a bunch of warnings. If you can post the compile errors in the chat, what you're seeing, that might help. We can probably help with some of this. Hopefully at this point you didn't modify any code. Oh, somebody got the audio buffer overrun. So that can happen if you're using a debug configuration instead of release. You'll probably see that if you've tried to train, if you try to classify more than two models, or sorry, two keywords, you'll probably see that. So try maybe going back and training just one. Yeah, if you're running into problems with this before trying to build, if you go back to this, my GitHub repo here. If you go into embedded demos, STM32 Cube IDE, the Nucleo-L476, this gives you the exact steps you need to perform. Yes, yeah, make sure you're not doing a debug build. That will definitely, it'll run, but it will definitely overflow your buffer. So once you've gotten this where it says debugger connection lost, shutting down, remember we did release here. We're not doing debug. We're specifically saying do not do debugging for us. So it's okay that it does this. We're not doing blinky. We're not going to press run here or anything like this. So you cannot do more than two. My experience, this is what I think I mentioned earlier, that when you were picking keywords, try 3. I can't promise they're going to work because the model may become too big and it might take too long to process that you start overrunning your buffer. This is one of those cases where like, oh, you want to do 3? Well, you need a bigger processor. So that's why I stick to 1 or 2 during this. So open up a serial connection. Because Windows, I need to go to Device Manager. COM ports, I'm on COM 7. Serial, connect with your serial of choice. Use 115200. And you should see all of that being spit out. This is your probabilities. Remember I mentioned earlier, you have the probabilities of each class. Noise, your background noise, unknown is it doesn't know what you're saying, and then the 2 classes that you picked. So I'm going to try saying house, and that should go up. You saw that briefly flash to like 98%. 0. So you'll see that yes flashed here, and that's because of the demo code. That is because of the demo code that I totally thought I checked into GitHub last night and did not check in. Still works, but what's going on here is if it sees classification label number 3 or index 3, it's going to print this, which corresponds to whatever your thing was. And I'll show you how to find those. So if you go to model parameters, model metadata, here is where your classes are listed in this order. So noise is 0, 1, 2, and 3. So if I want to print 0, I need to do 3. And actually, in fact, I recommend pulling out this and going above here. Because this where it prints out the results only happens once every 4 classifications, every second. We want it to do it faster. So what did I say 3 was? I forget. 0. So I'm actually going to change this to 0. This is your onboard LED. I'm going to pull this out and drop this right here. So let's have it flash the onboard LED for house. So that's 0, 1, 2. So I'm going to change my index to 2. So anytime that value, the output probability is above 0.5, which is my threshold, and I can adjust that, right? I can make it 80% to be a little higher. And then so every time it hears house, and so every time it hears 0, I'm going to build project. So every time it hits 0, then it should print 0 to the console. Every time it hears house, it should then flash the onboard LED. So everybody can give that a shot. Remember, indexes 0 and 1 correspond to noise and unknown. So you really probably want to play with indexes 2 and 3. And I'm going to project run. That should upload it to my board. Serial baud rate is 115,200. I don't know if it matters. I think there's some auto baud thing going on there, but 115,200 should work. It's using that embed. It's got that embed. It's got that embed programmer chip on the Nucleo board, which I think auto bauds. So, but 115,200 works. And I've absolutely lost my clock, and I've got 8 minutes left. Woo! So this is the end. I'm gonna bring up this last side while, oh, here we go. I can give this demo. All right, here we go. So we've got it going here. I'm gonna say something. House. You probably can't see it, but here we go. House. See how it's lighting up the little LED right here whenever I say it. I'll make my screen bigger for that. 0. 0. There it goes. 0. 0. It doesn't like that one. 0. Ah, there we go. So you can see those flying by. I'm going to stop sharing for a second here so that everyone can hopefully see me. And I can bring this up and house. 0, which won't do anything. House. Yeah, there we go. So we got to Blinky in the most roundabout, hardest, most obnoxious way possible. Let's share my screen again, and I'm going to come back to this final slide where we have 7 minutes. You're triggering mine with 0 fairly reliably. Awesome. So people were asking about this sliding window. I skipped a bunch of these slides because I thought we were like really limited on time. But yes, that's essentially what's going on is the sliding window. And we're comparing the probabilities here. So this was just what was going on with that sliding window. And I can burn through this real quickly. Boop, 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 right? And then once it sees that keyword, it compares that probability and we do something with that. So we've already run it. Here is the end slide. So I have like 2 minutes to go through this. Feel free to modify that code and play around with it if you're comfortable with STM32 stuff. I gave you a couple of examples for like how do you blink the onboard LED. This is what it should have looked like. Once again, I thought I committed, and this is why I should always check my repo to make sure I did commit those changes. Some resources to play around with. Here's the data sheet and the HAL API if you want to take a look at those. And yeah, there's the Hangout bit. I think that is on my project link, as well as Twitter handle, LinkedIn. If you want to chat with me, I do try to answer tweets. So that is all I have. I'll leave this up for a bit. Are there any questions? Do you recommend any more powerful boards for edge inference? Honestly, it depends on your application because that's always the answer, right? For audio, I wouldn't do anything less than like these ARM Cortex M4s, which I think is what we've got. Is there M4s or M4 pluses? I don't remember. But M4, I wouldn't go anything less than like an M4. When you start getting into like more hardcore audio processing, video processing or image processing, I'd move up to like the what are they, the M7s. I'd go a little more powerful. So these are running at like 80-ish megahertz, if I remember, something at like 80, 100 megahertz. So that's kind of where you start with audio. You can do less for that. So I've gotten stuff. You can do like some really basic anomaly detection in things like M0s, like really basic for like accelerometer. Like you don't read a ton. You do like basic Fourier transform. If you're not need to be really fast, you can get it done with like an M0. I think you did push it. I pulled it from GitHub and got it that way. Maybe I opened the wrong one when I downloaded it. So, okay, I'm glad that worked for people. Okay, good, I did. And so that must have meant I pulled the wrong one for my download and didn't clear my downloads last night. What would the Teensy 4 be able to do? I forget the specs on that, but if I remember, that thing is a beast. It was like 400 megahertz or something. You can probably start doing video stuff on that. Very basic, kind of like the, check out the OpenMV. TensorFlow Lite, they've got TensorFlow Lite running on the OpenMV with like MicroPython. Will you add Arduino side on the GitHub? Yes, that is like the next plan once I get, it's going to be the Arduino Sense, the BLE Sense. But honestly, if you like download the like Arduino package for the BLE Sense from like everything we did up until that point where we clicked the C++, if you just click the Arduino one and then go read how you import that into your Arduino, that will totally work for everything we just did. Go read how it works for Edge Impulse to import a Arduino library. So everything we did applies to Arduino. But yeah, I should hopefully include that. I managed to get TF Lite running on the, oh, that's awesome. Yeah, the Teensy, I haven't played with it. I think I've got a Teensy 4, but that thing is blazingly fast. What if I don't have STM32? This should still work. Like this supports most ARM, the C++ library is supported on most ARM processors. It's just a question of like, how well do you know the whole tool chain and the build process? Like I happen to know STM32 decently well, which is why I chose it, that or Arduino. Run configuration was debug. Yeah, sometimes that messes up, which is why I always check that. So yeah, make sure it's release. Yay, people are getting it to work. 600 megahertz for the Teensy. That's awesome. Can we use it? Yes, once again, the C++ library should compile. It doesn't, so it's not, it's that, can't remember the name of the processor inside of the ESP32, but it's not an ARM. The C++ library should work. However, note that when you download it from Edge Impulse, it enables some of the ARM specific CMSys stuff for doing DSP. The extensive, thank you, Tensilica. That's the one. I couldn't remember that name. It's enabling the ARM CMSys for DSP to allow those to go faster, and it's using the built-in hardware for DSP functions. So as long as those are disabled, that C++ library you download from Edge Impulse should run on it should compile for any microcontroller. It's just a question of, is it going to be fast enough without those hardware accelerators? Briefest explanation of how to retrain the model for better accuracy. So in Edge Impulse, all you need to do, go back to your neural, assuming you have the data, you don't want to add more data. What you want to go back to, assuming you have the data, you don't need to add more data, and you've got all the features extraction, just go back to your neural network classifier and just start playing with these parameters. So once again, how do you get better accuracy? You just play with stuff, you tweak stuff, you read a bunch of documents and say like, oh, I kind of have an understanding that maybe I need less neurons here, but more layers. Sometimes that works better. So really it's just starting to play with some of these, maybe try a two-dimensional convolutional neural network. And by the way, before I forget, if you're familiar with Keras, you can click this and you can go to Keras mode. So you can look at how they're building this model programmatically. I don't believe they give you ways to, oh, you can select the like learning rate, loss functions and all of that here. Okay, so yeah, you can, if you know Keras, you can adjust all of this programmatically here. But yeah, feel free to, and then once you've like changed this, just click start training again. It'll just train the model and give you an output. So just, write down what your accuracy was. And then keep in mind, if you start using the model testing or the model testing your test data to update your, to like look at and be like, oh, it overfit and then come back, you start introducing bias into your data. So there's like papers out there of like, how do you prevent that? But that's a good way to start. Like go to your model testing, use the unseen data, make sure it's working decently well, come back and do your update your parameters. Just know that you're introducing bias into your model every time you're doing that. Reduce training cycles from 100 to 30, decreased from 50. Sometimes it made it better for me and sometimes it makes it worse. Like I wish I knew exactly what was going on in the neural networks for that. Awesome. Yeah, go have fun. Play around with it. I hope this has given you everybody a start for this kind of stuff. It's a lot to take in. If you really want to get down to the nitty gritty and do some math, Andrew Ng's course, highly recommend on Coursera. That's what I started with. And then there's like a bunch of books out there that you can start going through. And then I would make sure you do that. I would learn Keras once you're familiar with that. And then once you're kind of comfortable training your own networks and like, building them or at least pulling them off the internet and tweaking them, then I would jump into like, Pete Warden and Daniel Sitsunayaki's TinyML book, because that jumps into how to use the TensorFlow library directly on a microcontroller. And Edge Impulse is basically take that and wrapped it up into a library for us that like works off the shelf, which is why I chose that for this, where we only had 2 hours.
Well, Sorry, I don't mean to interrupt, but Shawn, thank you for sharing with us this really enlightening and helpful presentation. It was very technical, but you presented it in a pretty uncomplicated way. So, and it was also very entertaining. And thank you for making it a very down-to-earth and personable talk. So I'd like to invite everyone to continue with the conversation for comments and questions at your hackaday.io page. You can go use the public chat for more talks. I posted the link in the conversation or in the chat sidebar. And with that, thank all of you for being a part of this amazing community and joining us for Emoticon. So I look forward to seeing more of you at other talks. And yeah, so appreciate it. Thank you again, Shawn.
Thank you. Thanks, everybody.
All right.